newly installed cameras capturing an eruption from the Black Diamond Pool at Yellowstone National Park on Saturday.
Now to the extraordinary images tonight, the scare for visitors at Yellowstone National Park.
Beneath the expansive blue of the Montana sky, steam rises in ghostly columns, and the land pulses with energy, both seen and unseen. Yellowstone National Park. Just the name conjures images of fire and transformation.
Eruption at Yellowstone National Park in Wyoming Saturday, all of it caught on camera. A new webcam captured this only weeks after it was installed to track activity at the Black Diamond Pool in Biscuit Basin.
Of boiling pools and powerful history, it is the ultimate North American cauldron, a supervolcano whose eruptions have shaped entire eons. But in these early months of 2025, Yellowstone's evolving story is being rewritten not by the ground's trembling or by plumes of ash, but by the calm and far-reaching eyes of satellites from hundreds of miles above the Earth, where silence rules and perspective is vast. Landsat satellites sweep their sophisticated sensors across the park. Their vision reveals a Yellowstone transformed. Beneath the apparent calm, pools and basins glow with infrared radiance, each a sign of shifting heat and restless depths, particularly in the northeastern quarter, where geologists now suspect future volcanic activity might be most likely. The park reveals new secrets. Here, the Landsat data captures not mere flickers, but persistent surges of energy, sometimes measured at 40 or even up to 74 megawatts, a silent, ongoing output. What does it mean to identify, in this wild landscape, a geothermal radiant power output of 40 megawatts, even rising occasionally to 74? What ancient stories dwell in the interplay of water, rock, and underground heat? As technology sharpens and science advances, the ancient puzzle of Yellowstone's hydrothermal system comes into ever clearer focus. The tools of modern monitoring allow us to see what eyes cannot, the real-time shifts and flows of energy underneath one of the most famous volcanoes in the world. But does this growing clarity grant us greater safety? Or does it merely reveal new puzzles, new questions, new depths to the unknown? The heat within, mapping Yellowstone's fiery power. To understand the meaning of Yellowstone's heat, one must think beyond the steam-shrouded pools and sulfur-scented air. On the ground, over 10,000 thermal features span more than 120 areas, each a stage for boiling water and strange, vibrant chemistry. But these captivating scenes are only fragments. Beneath them lies the driving force, the vast, buried magma chamber that curves the land and fuels the dynamics above. In 2025, it is the Landsat satellites that become our newest cartographers of this hidden world. With daily passes, they track not merely surface conditions, but radiant energy, the warmth that seeps from deep within, marking patterns and changes invisible to unaided senses. This energy is measured not in dramatic flashes, but in the steady outpouring of megawatts, sometimes surging, sometimes fading, but always significant. When considered in context, 40 megawatts, sometimes climbing to 74, means a remarkable amount of thermal energy is being vented. Enough, in any given moment, to power thousands of homes. Enough, cumulatively, to rival complex industrial systems. When scientists add up the geothermal radiant power across the entire sweep of Yellowstone's 120 thermal areas, the result ranges from 1,500 to 3,100 megawatts, a sum that matches the electrical demands of sizable cities. Each basin is different. Lower Geyser Basin, for instance, is known for particularly vigorous activity, sometimes reaching pixel temperatures in thermal images of up to 32 degrees Celsius above the surroundings. Each basin shows a distinctive signature, patterns of higher and lower output, shifting in rhythm with time, and perhaps with deeper movements far below. But what is it truly that feeds this persistent fever, this ever-present warmth emerging from the depths? Is it the natural diffusion of heat through the Earth's cooling rocks? Or could it be signals of fresh magma, volatile and dynamic, making its way upward? Such are the questions that now drive researchers, linking surface observations with the ageless processes below. Eyes in the sky, how Landsat sees Yellowstone's secrets. For many decades, Yellowstone's mysteries eluded easy answers. On the ground, in the swirling mists and warning signs, geologists measured and waited, tested waters, and hoped to catch the Earth in a moment of openness. Seismic networks tuned in, listening for the faintest quakes. Gas sensors picked up the trace chemicals whispered from below. Yet for all these tools, much of the park's underlying thermal system remained obscure, intangible at park-wide scales. Now, Landsat, that patient observer from space, serves as Yellowstone's vigilant sentinel. Each orbit brings a harvest of new data, heat signatures mapped onto the landscape, colored visualizations that reveal not just the location, but the behavior of features over time. In 2025, with improvements in data resolution and analysis, these readings are converted quickly into practical insights, allowing even subtle shifts to be monitored closely across the entire ecosystem. The northeastern clusters, for example, have seen increased scientific attention. Recent research and satellite imagery combine to suggest that these areas might be most likely to host future eruptions, should any occur. Thermal data from these zones reveal persistent, localized warmth. Pools like Turbid Lake, just north of the vast Yellowstone Lake, are continually tracked, not just for their dramatic appearances, but for their measurable effect on the overall geothermal budget. The power of satellite observation lies in its reach. A sudden anomaly, a spike in the thermal pixel value of a remote feature, a brightening in a distant geyser, a slow expansion of geothermal area can all now be identified quickly. It is as if the 50-mile-wide caldera has become a living chart of fluctuating heat, rendered visible for the first time. Despite all this, questions remain. Why are some basins, such as Lower Geyser Basin, so volatile in their energy output? What governs the surges from 40 to 74 megawatts in a matter of weeks? Do such shifts reflect only seasonal cycles, or are they harbingers of movements far below ground, perhaps of changes in the flow of heat and gases, perhaps even signs of fresh magma migrating upward? These are the mysteries that satellite data frames, if not resolved. The ghosts of July, explosions, eruptions, and the power beneath. Yellowstone's appearance of tranquility is fragile. The summer of 2024 reminded observers of this power. On July 23rd, Black Diamond Pool, a usually placid spring in Biscuit Basin, erupted suddenly in a hydrothermal explosion. The event, captured on video for the first time, was a forceful interruption. Rocks flung, water roaring, steam billowing into the sky. The area was quickly closed, while scientists and new webcams recorded the aftermath. The significance of such events extends far beyond spectacle. The explosion delivered rare data, close-range seismic signatures, gas pulses, and a real-time thermal map of how the landscape responded. For several days after, Landsat satellites traced the residual heat, the radiance still well above background, evidence of how energy lingers and flows after such forceful events. For the scientific community, every explosion is both a puzzle and a warning. What tipped Black Diamond Pool from steady bubbling to violent eruption? Was it a sudden buildup of pressure, a clog in the deeply branching hydrothermal conduits, or an injection of new heat from the deeper crust? Each potential answer points to new areas of study. Each incident renews the need for careful, continuous monitoring. Hydrothermal explosions are, of course, distinct from volcanic eruptions. They reflect shifts in underground pressure and plumbing, rather than the movement of magma itself. But when the numbers leap, when a thermal area's radiant output jumps, as it did at Black Diamond Pool, the change is measurable both in short-lived bursts and in longer-term patterns as seen from space. These readings remind us Yellowstone's geothermal power is not just a curiosity, but a living force capable of altering landscapes in moments. Inside the volatile-rich cap, clues to Yellowstone's future. To understand what lies beneath these remarkable outputs, scientists must look deeper. Remote sensing, Seismic exploration and geochemical analyses now combine to form an evolving picture of Yellowstone's inner workings. Recent research points to the presence of a volatile-rich cap, a zone heavily charged with water, carbon dioxide, sulfur, and partially molten material, all perched atop the immense magma reservoir below. Inside this zone, complex interactions between pressure, temperature, and material state give rise to instability. The springs, pools, and geysers are the visible, surface-level symptoms of this volatile mix. The radiance captured by satellites, the oscillations in output from basin to basin, represent not just mere changes above ground, but hint at vigorous, ongoing processes below. Significantly, new studies propose that the northeastern quadrant of Yellowstone now appears more likely to host future eruptions, a revision of earlier maps that treated the risk as more evenly spread. This hypothesis is strengthened both by geological mapping and by remote sensing. Increased and persistent heat output is registering in those areas. While these increases are modest in absolute terms, their consistency has drawn close attention, yet interpretation remains challenging. Is the volatile-rich cap acting as a kind of pressure relief, venting energy incrementally and safely to the surface? Or is it instead a slowly hardening seal, with the potential to trap energy and generate larger events if breached? Each reading from Landsat, each degree of temperature change, functions as a clue, but never as an answer in itself. Patterns from above show that the system breathes. Radiant output naturally fluctuates through the seasons, but more abrupt jumps, like shifts from 40 to 74 megawatts, might indicate reorganization of the subsurface fluid pathways, or transient pulses of heat or gas. The line between normal variability and signals of unrest is finely drawn, discernible only through long-term records and careful analysis. Patterns and power. Yellowstone's numbers decoded. To the public, the vast numbers that define Yellowstone can seem abstract, yet when contextualized, they highlight the magnitude and uniqueness of the park's processes. The 120 thermal areas, encompassing over 10,000 features, collectively vent enormous amounts of geothermal energy. The park's total geothermal radiant power output, measured across all areas, is estimated between 1,500 and 3,100 megawatts. These are industrial-scale numbers, equating to multiple large power stations running simultaneously. Within this complex, distinctive features stand out. Lower Geyser Basin, for example, displays particularly high radiant power, often between 40 and 74 megawatts. Its hottest features register temperatures up to 32 degrees Celsius above their surroundings, radiating strongly in the eyes of the orbiting satellites. Each basin, each feature, contributes to a complex mosaic of power and variability that forms the living core of Yellowstone. Among the lakes, Turbid Lake, just north of Yellowstone Lake, is the largest of its kind in the region and serves as a marker in satellite thermal monitoring. Persistent, low to moderate heat signatures are not always visually dramatic, but are now tracked alongside more prominent features, further enriching the data set. Energy from these lakes and basins, even when not immediately spectacular, contributes to the overall geothermal character of the park. When these values are tracked over time, essential patterns emerge. Heat builds to crescendos in some features, lulls in others. No 2 years yield exactly the same thermal topography. Satellite and ground data combine track not just the averages, but also the outliers, pools whose output fluctuates rapidly, zones that suddenly brighten or fade. Science, leveraging this wealth of data, works steadily to translate the numbers into meaning. Still, a degree of uncertainty is inevitable. Are the cycles and surges merely the natural breath of Yellowstone, or might they mark preparation for events not yet visible? At present, most energy surges are understood as a combination of seasonal change, shifts in underground water pathways, and minor reorganization in the hydrothermal system. Dramatic changes are closely watched, but are as yet not considered precursors to eruptive activity. Nonetheless, the emphasis on high resolution and frequent observation is a response to the dynamic reality of the region. Echoes of catastrophe, Yellowstone in historical imagination. Few landscapes occupy so storied a place in North American consciousness as Yellowstone. The vast caldera, its boundaries marked by past supereruptions, invites reflection on timescales far longer than human memory. Layers of ash and deeply scarred rocks remind us that under this beauty lies a history of immense upheaval. In recent years, episodes of seismic swarms, dozens of tiny earthquakes in the vicinity of thermal zones have brought renewed scientific attention. While such swarms, often of magnitude 1.8 or less, are not themselves alarming, they provide further evidence that the system is restless and interconnected. For now, according to expert consensus, there is not enough molten rock near the surface to threaten any major eruption. The mythology of Yellowstone is not baseless. The stories of its explosive history are supported by geology, yet the reality today is one of ongoing, small-scale change, not immediate threat. Landsat's role in this context is dual. It serves as a chronicler, capturing the minute surges and lulls that might otherwise pass unseen, and as a reassurance, reminding us that the region is watched and measured more closely than ever. The narrative that emerges from the numbers is not one of imminent disaster, but of complex stability, a system constantly in motion, constantly monitored, with a deep past and a closely scrutinized present. The silent watch, science, preparedness, and the future. If Yellowstone is a window into the Earth's deep processes, then the era of satellite and technological monitoring brings that view into ever sharper relief. Each new thermal dataset, every signal above background, is a piece of a long-term record that guides planning and response. Monthly updates from the Yellowstone Volcano Observatory translate satellite readings and ground-based findings into public messaging and technical advice. Park management is shaped by these outputs. Routes are assessed, warnings are issued, and research priorities are set in line with the evolving picture of geothermal activity. Webcams, such as those at Biscuit Basin, installed after the 2024 explosion, provide continual observation. Drones and mobile thermal sensors gather fine-scale data in areas inaccessible or hazardous for field teams. Together, these technologies create a multi-layered shield of observation, designed not only to detect change, but to inform how it is handled. The approach is not one of fear, but of informed respect. Both science and local communities have come to understand that while Yellowstone is iconic and wondrous, it demands careful stewardship. The balance between curiosity and caution, between research and readiness, is renewed with every fresh set of readings. Yet even as understanding grows, some questions are destined to remain. Is what we see now, these cycles of surges and lulls, a sign of health, of a well-ventilated system? Or could some fluctuations be the earliest indicators of structural change within the park's vast, hidden heart? These uncertainties drive ongoing research, funded and managed in the face of economic and political realities. The deep rhythm, Yellowstone's living map. At the heart of Yellowstone, the measurements collected from satellites and ground instruments reveal patterns both precise and mysterious. The mapped flows of thermal energy, rising, peaking, fading, compose a kind of music, a rhythmic pulse, signaling the continuous negotiation between Earth, water, and magma. Researchers correlate surges in radiant output with seismic records, with gas emissions, and with thermal imaging on the ground and from above. The hope is to build an integrated model of the system's behavior, one that accounts for both gradual adjustments and rare, sudden events. This living map is invaluable not only for its scientific insight, but for its broader lessons. As global volatility increases and the unpredictability of natural systems becomes ever more relevant, Yellowstone's culture of vigilance and humility before the unknown becomes a model. Small and seemingly isolated pulses, such as a minor flare in a distant pool, echo the potential for change everywhere in nature. Landsat's revelations have redefined the scientific quest, the knowledge that lets us predict, prepare, and adapt. In this ongoing epic, each new datum, each new megawatt measured, is a part of the larger, ever unfinished story written in stone. Between the lines, unanswered questions, unfinished stories. What are we to make of these discoveries? A measurable output of 40 megawatts, rising to 74, traced from orbit across a region etched into legend. For many, these numbers are a comfort. The energy is vented steadily, the system is actively monitored, and the risks are known and managed to the best of contemporary science. There is currently no evidence for imminent danger, no sign of a major eruption or widespread upheaval. Leading experts emphasize that, while the system is very much alive, there is not at present enough accessible molten rock to fuel the catastrophic scenarios of imagination. For others, the rich detail of current monitoring provokes new questions. Do the observed anomalies, the persistent heat in the northeast, or the fresh memory of Black Diamond Pool's violent eruption point to simmering possibilities not yet understood? The extent of the volatile-rich cap and minor shifts in energy output are reminders that Yellowstone's underground system is complex and only partially deciphered. We now live in a world where the Earth's signals can be measured in almost real time, but interpretation is always a challenge. Knowledge is never final. If we could map every lake and basin by energy flux, what else might we discover? How much remains out of reach? Science in Yellowstone is always a work in progress. Observation, hypothesis, and adaptation. Each pulse, each rise in radiant output brings new context, new questions, and a deeper appreciation for the system's richness and resilience. The story is ongoing, its chapters still unfolding at the pace of geothermal time. The next signal. Today, steam continues to drift above Biscuit Basin, a quiet testament to the heat below. The park is alive, its every watt of radiant power, a line in the ever-expanding narrative of Earth's energy and change. In the ongoing interplay between measurable radiant output and volcanic history, we are both scholars and subjects. Are we, perhaps, finally learning the lessons inscribed in the deep processes of our world? Or are we simply bearing witness, as humans always have, to the complex and irreducible dance of nature? If you want to follow each pulse and flicker from Yellowstone's hidden machinery, stay tuned for more insights, from radiant surges to subtle seismic shifts. Every pool, every plume, every watt of energy measured by the patient eyes of satellites is a testament to the enduring truth. Here, the story is never finished.